Lecture 4 begins. The subject of lecture 4 is heat transfer and mass transfer. I'll explain the heat transfer first, then the mass transfer. You'll find that the treatment of these two transfers are very similar. Thermodynamics has a long history as well as fluid dynamics. And thermodynamics has two aspects. One is science-oriented and the other is engineering-oriented. Heat transfer belongs to the latter. In general, engineering problems are so complicated that the application of purely theoretical approach is limited. So in the field of heat transfer, various formulas have been derived semi-empirically based on experimental fact to deal with various industrial problems. The interaction between the particle phase and the fluid phase is called phase coupling or phase transport phenomena. In lecture 1, I have used the word phase coupling, but from here on, I will use the word transport or transfer instead of coupling. There are three types of transport phenomena: momentum transfer, heat transfer, and mass transfer. Heat and mass conduct or diffuse within a single substance, but what is important in multiphase flow is transfer between two different substances, such as a solid particle and fluid. The momentum transfer is caused by the difference in momentum between the particle and the fluid. The momentum transfer takes the form of fluid drag. The drag is proportional to velocity difference. The heat transfer is caused by the temperature difference between the particle and the fluid. Mass transfer is caused by the difference between the mass fraction of the substance on the particle surface and mass fraction in the fluid. The formulation of the three transfers follows the same pattern as shown by the three yellow frame in this slide. Transported quantities such as momentum, heat, and mass are proportional to the difference in the quantities between two substances. Empirical coefficients are put on before the term of difference. As explained in the lecture 3, there are various empirical formulas for drag coefficient. In the case of heat and mass transfer, more formulas come out than the case of momentum transfer. This gives us an image that the treatment of heat and mass transfer is quite complicated, and so many people don't like to work in this field. However, as I said, the formation of these transport phenomena follow the same pattern or style. Once you know the pattern, understanding is not so difficult. I believe so. To understand the lecture 4, you should have the minimum knowledge of some technical words and unit of heat. First, I will speak about the Geothermal experiment. You must have learned it in high school physics. Geothermal found that the heat quantity and the mechanical work are equivalent. So the heat and the work are given the same unit of joule when expressing their quantities. 1 joule is the work required for 1 meter displacement by the force 1 Newton. Before, the heat quantity had the unit of kilocalorie. 1 kilocalorie is the heat quantity required to raise 1 kilogram of pure water by 1 degree of Celsius. Kilocalorie and calorie are not SI unit, and so it is not used now in the field of science and engineering. Conversion formula shows that 1 kilocalorie is equal to 4,185.5 joule. Work part-time and heat quantity part-time have the same unit, that is joule per second or Newton meter per second or watt. Work part-time is called power. Heat quantity moving per unit time and per unit area is the heat flux. Its unit is joule per square meter or watt over square meter. The heat quantity required to raise the temperature of 1 kilogram substance by 1 Kelvin is defined as specific heat. The temperature of 1 Kelvin is the same as 1 degree of Celsius. The unit of specific heat is joule over kilogram Kelvin. The specific heat of water is 4,185.5 joule per kilogram Kelvin. This value is the same as the work equivalent of heat. The specific heat of iron is 445 joule per kilogram Kelvin. In the case of a gas, such as air, the specific heat differs depending on whether the temperature is raised with constant internal pressure or with constant internal volume. The specific heat with constant internal pressure is called constant pressure specific heat, and specific heat with constant internal volume is called constant volume specific heat. When the heat is added under constant pressure, the internal gas expands. Expansion means that the gas exerts a force on the outside. In the case of constant pressure, the heat supplied to gas is spent not only on the internal temperature rise, but also on mechanical work. So the constant pressure specific heat is larger than the constant volume specific heat. The specific heat and the heat quantity required to raise the temperature of 1 molar substance by 1 Kelvin is called molar specific heat. In the field of chemistry, molar specific heat is common. Heat flux is defined in the last slide as heat quantity per unit time and unit area. Its unit is joule over square meter or watt over square meter, and its symbol is small q dot here. Movement of thermal energy takes the form of heat conduction or heat transfer. Heat conduction is the move of heat from a hot zone to a cold zone in a single substance. Heat transfer is the transfer of heat between two different substances such as solid and fluid. Regarding the heat conduction, we have the well-known Fourier's law. According to the Fourier's law, the heat flux of Qf dot due to conduction is proportional to the thermal conductivity Kf and temperature gradient with minus sign. The thermal conductivity Kf is a physical property of a substance. The unit of the thermal conductivity is watt over meter Kelvin. The table on the right shows a few examples of the thermal conductivity. The thermal conductivity of air is very low, and that of copper is very high. The heat flux Qt dot due to transfer is said to be proportional to the heat transfer coefficient Ht and temperature difference between fluid temperature Tf and particle temperature Tp. The direction of heat transfer is determined by the relationship between temperature Tf and Tp. The unit of heat transfer coefficient Ht is watt over square meter Kelvin. The heat transfer coefficient Ht is not a physical property, but varies depending on the condition of the fluid surrounding the particles. For example, when the fluid convects around the particles, the coefficient Ht increases. Various empirical formulas of Ht are available. In this slide and next slide, I will show how empirical formulas of heat transfer coefficient Ht is derived. It is assumed that that the particle is a sphere with a diameter d. See the definition of heat conduction and heat transfer. Multiplying the small qf dot by the area of the sphere surrounding the particle gives the large qf dot as shown on the second line. Please note the symbol large r. Symbol large r is the radial distance from the sphere to the fluid space. The large qf dot is the heat quantity per time from the hot zone to the cold zone when the fluid does not convection. Large qf dot is constant because it does not increase or decrease in the fluid. This equation is regarded as differential equation for temperature T. By integrating the differential equation with the surface temperature and the fluid temperature far from the surface as the boundary condition, it is found that heat quantity per time large qf dot is determined by the temperature difference and the thermal conductivity kf as shown on the fourth line. When the fluid does not convection, the quantity of heat transfer is equal to the quantity of heat conduction. But fluid convection promotes the heat transfer, and so the quantity of heat transfer Qt dot is larger than the quantity of heat conduction. Next, move on to the heat transfer. Multiplying the heat transfer equation by the particle surface area gives the heat quantity Qt dot. As I said over again, if the fluid does not convection, the quantity of heat transfer is equal to the quantity of heat conduction. As a result, Qt dot equal to Qf dot, and heat transfer coefficient Ht is expressed as Ht is equal to 2kf by d, as shown on the seventh line. If the fluid convections, the quantity of heat transfer will be larger than the quantity of heat conduction. So Ht is larger than 2kf by d, as shown on the eighth line. Such heat transfer is called convective heat transfer. Therefore, the general formula for the heat transfer coefficient is expressed by multiplying the kf by d by an empirical coefficient nu. The coefficient nu is called the Nusselt number after the researcher's name. When the fluid does not convection, the Nusselt number have the minimum value 2. The result of the last slide is summarized on the first line of the slide. Here, 2 examples of empirical formulas for the Nusselt number of a sphere are shown. The second and subsequent terms on the right-hand side indicate the effect of convection. In both equations, Nusselt number is equal to 2 at the limit when the random number approaches 0. An non-dimensional number called Prandtl number appears in the empirical formula that gives the convection effect. I will explain the Prandtl number below. For that purpose, let's consider the diffusion equation. The diffusion equation expresses how substances and physical quantities diffuse in space over time. The derivation of this equation is omitted here to save time. First, the momentum diffusion equation is shown. The time derivative of the fluid velocity is proportional to the Laplacian u and the momentum diffusivity nu. I have explained the Laplacian operator in the lecture 2. This equation is the same as the Navier-Stokes equation without the convection term and pressure term. When the fluid velocity diffuses due to the viscosity effect, the velocity changes according to this equation. The kinematic viscosity is momentum diffusivity. Another well-known diffusion equation is the heat conduction equation. The time derivative of temperature T is proportional to the Laplacian T and the thermal diffusivity. The word of thermal diffusivity and thermal conductivity are similar, but be careful about the difference between these 2 words. The thermal diffusivity is given by the thermal conductivity, fluid density, and specific heat as shown in the red line frame. The Prandtl number is defined as a ratio of the momentum diffusivity to the thermal diffusivity. Substituting the expression of the thermal diffusivity in the red line frame, the Prandtl number is given by the expression in the second yellow frame. Next, let's derive the equation of particle temperature. Large Qt dot is the heat quantity per time. As shown before, the large Qt dot is expressed in the equation on the first line. Substituting the heat transfer coefficient HT into the equation Qt dot, that Qt dot is expressed by the equation on the second line. The Qt dot makes the particle temperature change, increase or decrease. This change depends on the particle properties such as mass and specific heat. The Qt dot can be expressed by the time derivative of particle temperature dTp by dt multiplied by specific heat and particle mass. When the Qt dot is positive, Tp is larger than Tf and the particle temperature will decrease. So the minus sign is put in this expression. Substituting this expression into the equation on the second line, the change in particle temperature over time is expressed by this equation shown in the yellow frame on the third line. Note the symbol here. So far, the symbol small m has been used for the particle mass, but in this lecture, large M is used for the particle mass. The symbol small m is used for the particle mass divided by the surface areas. In lecture 3, we consider the momentum response time when the random number is small. The thermal response time can be discussed in the same way as the momentum response time. To find the thermal response time when the random number is small, first set Nusselt number equal to 2 and substitute the particle mass large N given on the first line into the equation of particle temperature. Then the thermal response time is obtained in the red line frame on the fifth line. The equation of the particle temperature takes a simple form. In lecture 3, I have presented the equation of particle motion using the momentum response time tau v. The equation is shown in the right margin for comparison. By integrating the equation in the second line, in the second yellow frame with the initial condition that Tp equal Tp0 at t equals 0, the equation on the last yellow frame is obtained. This expansion of this kind of equation is same as in the case of particle motion. Let's see the momentum and thermal responses of a polyethylene particle with a particle size of 100 microns and specific gravity of 0.95. Let's see how the response differed between the two cases when the particle is in the air and when it is in the water. The physical properties of particle, air, and water are shown in the left column. These physical properties are substituted into the equation for the response time obtained so far. Then the ratio of the thermal response time tau t and the momentum response time tau v is expressed by the top equation in the right column. It is found that ratio becomes 3 second time Prandtl number. The Prandtl number in the air is 1.57. So the tau t over tau v is equal to 2.36. That is, thermal response time is 2.36 times the momentum response time. The Prandtl number in the water is 3.704. So tau t over tau v equal to 5.56. That is, thermal response time is 5.56 times the momentum response time. It is found that the response to heat is slower than the response to momentum. In other words, temperature equilibrium is achieved more slowly than the velocity equilibrium. This tendency is especially remarkable when the particle is in water. Next, I will explain the mass transfer and mass diffusion. The treatment mass diffusion and mass transfer is almost the same as heat conduction and heat transfer. mass diffusion corresponds to heat conduction. The diffusion quantity is proportional to the gradient of substance density or the mass fraction, and it is determined by the physical properties of substance. Mass transfer corresponds to heat transfer. Mass transfer is the transfer of substance crossing from one substance to another substance to uniform density. As in the case of heat transfer, the quantity of mass transfer is promoted by convection or dynamic motion of fluid. Mass diffusion is the movement of substance in the form of fluid from high density zone to the low density zone to uniform its density. Mass diffusion is caused by the thermal motion of molecules. So as long as there is non-uniform density distribution, the substance diffuses naturally. Mass transfer is the transfer of substance across the boundary between two different materials, such as solid and gas. If there is no flow convection, the quantity of substance conveyed in the fluid is the same as the quantity of mass diffusion. If the fluid has a convection motion, the quantity of transported substance is larger than the quantity of mass diffusion. The quantity of moving substance per unit time and unit area is called mass flux. The mass flux due to mass diffusion is represented by the symbol md dot. The fixed law is known for the mass diffusion. This law corresponds to Fourier's law of heat conduction. According to the fixed law, the mass flux md dot is equal to mass diffusivity nu times the gradient of substance density as shown in the equation on the first line. The mass diffusivity nu is the physical properties of substance, and so it is uniquely determined by the substance. Since there are multiple species in one substance, a subscript A is attached to the density symbol law to indicate the specific species. Furthermore, the density is made dimensionless by the fluid density law F of the free stream, as shown in the red circle. This omega A is the mass fraction of species A. Mass transfer is movement of a substance crossing from particle to fluid or from fluid to particle. Mass flux mt dot due to transfer is said to be proportional to the mass transport coefficient hd and mass fraction difference of omega F infinity far from the particle and omega as at the particle surface. This equation can be regarded as the definition of the mass transfer coefficient hd. As I said already, the quantity of mass transport is the same as quantity mass diffusion predicted by fixed law if the fluid does not convection. But usually the fluid makes convective motion around the particle, so the quantity of mass transfer is larger than the mass diffusion. The mass transfer coefficient will be derived by referring to the mass diffusivity, the fixed equation for mass diffusion, and the equation of mass transfer as shown again. From now on, it's assumed that particle is a sphere and phenomenon of diffusion and transfer is steady. Multiplying the small empty MD dot by the area of the sphere surrounding the particle gives the total quantity of substance flow per time. The total quantity per time are constant as shown on the first line. Please note the symbol large R is the radial distance from the sphere to the fluid space. Rewriting the equation on the first line, it becomes a differential equation with the mass fraction of species A as shown on the second line. Let's integrate the differential equation. The boundary conditions for integration are the mass fraction omega as on the particle surface and the mass fraction omega infinity far from the particle. The quantity of mass diffusion md dot can be obtained as shown on the third line. It is found that md dot is determined by the mass diffusivity d nu and the difference in mass fraction between the free stream and particle surface. This equation holds when the fluid does not convection. Multiplying the mass transfer equation by the surface area of the particle gives the quantity of mass transfer empty dot for the particle as shown on the fourth line. If the fluid does not convection, the mass transfer does not exceed the diffusion quantity. So empty dot is equal to md dot, and so the hd is equal to 2d nu over d. If the fluid convection, empty dot is larger than md dot, and thus hd is larger than 2d nu over d. So the general formula for the mass transfer coefficient hd has been established by multiplying d nu over d by the empirical coefficient sh. This coefficient sh is called Schau's number. Schau is also the name of the researcher. Similar to the Nusselt number, when the quantity of mass transfer is equal to the quantity of mass diffusion, sh is equal to 2. The Schau's number is generally defined this way. In the case of a sphere, the diameter is taken as the representative length. Here is an example of empirical formula for the Schau's number. It's very similar to the Nusselt number for the heat transfer coefficient. The Schmidt number appeared instead of Prandtl number. Schmidt number SH is a non-dimensional number defined by momentum diffusivity divided by the mass diffusivity. Comparing with the definition of the Prandtl number, you have found that both the Schmidt number and the Prandtl number are the ratio of the momentum diffusivity to the diffusivity of another physical quantity. In the Prandtl number, diffusivity compared with the momentum diffusivity is the thermal diffusivity, and in the Schmidt number, the diffusivity compared with the momentum diffusivity is the mass diffusivity. Using the Schau's number, equation of mass transfer per time is shown in the yellow frame. The particle mass increases or decreases depending on the relative magnitude of omega A infinity and omega AS. In this slide, I will explain the d square law. D square law concerns the time required for one droplet to evaporate into vapor. The d square law is derived from the equation obtained so far. The formula of mass transfer on the previous slide is shown on the first line. The droplet mass, large M, is the density low P times volume as shown in the left equation on the second line. By differentiating this left equation with time, the time derivative of droplet mass M can be expressed as the time derivative of the droplet diameter d. Substitute the derivative of the mass, droplet mass given by the derivative of the droplet diameter into the above equation on the first line. Then the differential equation of the diameter d is obtained as shown on the second line. The right-hand side of the above differential equation can be assumed constant approximately, so the differential equation can be integrated under the condition of initial condition d0 as shown on the third line. Lambda is a constant given on the left equation on the first line. By putting d equals 0 on the first line, the evaporation time tau m of the droplet can be obtained as shown on the fifth line. In the calculation of droplet evaporation, it is a little complicated problem how to estimate the value of mass fraction of particle surface. The mass fraction omega as can be calculated by the formula as shown on the sixth line. In this case, the diffusion substance is water vapor. Air is a mixture of nitrogen, oxygen, and other molecules, and the molecular weight of air is average value calculated from the molecular weight of those substances. Finally, the formula is shown that consider the latent heat of vaporization when the droplet evaporates. The latent heat is the heat quantity required when the fluid undergoes a phase change from the liquid to gas phase. The heat quantity per time is shown first. This equation is the temperature equation of a particle. The quantity of mass transfer per time is shown next. When the fluid undergoes a phase change from the liquid phase to the gas phase, the latent heat of vaporization due to mass transfer must be taken into consideration. Therefore, the temperature equation of the particle includes a term of latent heat. HL is the latent heat per mass. Substituting the expression of the mass transfer, the temperature equation becomes the equation in the yellow frame. This is the end of lecture 4. Thank you.